Now, oh, Albert, could you get the light, please? The light, the light. Thanks. Now, just to start here, the name of this section is stress and strain. Now, they're perhaps words you know from English already. What do you think the word stress and strain mean in English?
Pressure on an area.
Yeah, no, but even just informally, how would you use stress and strain?
Press. Press.
What do you mean? Give me an example. Give me an example of using stress and strain. Or stress or strain.
Like you're squishing someone's head.
Yes.
It's stressing.
It's quite stressful for them, yes.
Yeah, it's...
Anything else?
If, for example, his head is between you and your hand in the wall and you're pressing it.
This would be kickboxing style, wouldn't it? Yeah, that would be one. So like we're thinking of stress and strain as like you're grabbing something and you're pushing it. Yeah. You know, you're trying to... Or what are you trying to do when you put stress and strain on something? You're trying to change the shape. Yes?
Smash it.
Or break it, yeah. That's another thing. So stress and strain. You know, it's like when you're trying to push something or you're trying to pull something. And we've already seen this a little bit. Where have we seen this a little bit?
Harmonic.
Yeah, simple harmonic motion with the spring. So if I picture the spring for the moment. Yeah, Mustafa, we just started. So if I picture the spring. And if I try to move this, will this move easily? It depends on the spring, but normally when you picture a spring, can you move it easily? Yeah, you can. Now, what about something like a rope, like what I had here? Now, if you look carefully, you know, you can move it a little bit, but not really as much as a spring, right? So there's something kind of stronger about it. So we need to do some vocabulary to describe this. There's a few different words for it here. So I'll give you each one anyways. So maybe this one's more difficult to move. Okay, so firstly, strength. Okay. Now, I know we all know strength from English, right? What does to be strong mean? Yeah, you kind of like, how do you explain it? Yeah, no pointing to yourself now. Strength. You all know the word strong?
Yeah, power.
It's like power, yeah. Now, in physics, strength means, if you say something is strong, it means it's very difficult to break. So, for example, with my rope, would you say this is strong?
Yeah.
I think it's pretty strong, you know. But what about something that wouldn't be strong, like maybe the tissue or something? You know, if I try to do the same thing, oh, it's not so strong. So strength here means, if you say it's strong, it means it's difficult to break. That's what strength means in physics. Okay, so please write this down. This is the formal definition of strength in physics class. Okay, next one now.
Right.
Yeah, I'm just writing very short definitions here. You can add your own notes in, but basically the stronger it is, the more difficult it is to break it.
So, an example will be the repeat question, write the definition.
The definition of strength would be, okay, if you want to be a bit more formal, the force required to break it is how strong it is.
No, like that's good. No, like.
I'm just going to make a little there. Okay. So in other words, the stronger it is, the more difficult it is to break it, the more force you require to break it. And in the exam, when you give a definition, it's always good to give an example. So you should also say, what's an example of something with a lot of strength? You could say like a steel cable. You know, like in the elevator.
How about plastic?
Yeah, now plastic.
It's elastic, you can't break it as well.
Yeah, you see, this is when we're getting into different terms now. I think with plastic, it depends on the type. But like, I don't know, if I had...
This, I think this also plastic.
Yeah, this is, well, yeah. It's all different types of plastic. I'm trying to picture something like, I don't know, like if I have plastic arrow or something, or plastic a little plastic cable.
Plastic.
You know those little plastic... No, you know those like little plastic ties? You know, like if you have a cable
Yeah,
and you can tie some
The
plastic
white one,
around it.
yeah.
The white one, yeah. I think that's pretty strong.
No, you can't cut it.
No, if you try to, with force.
Yeah, sure you can.
You can.
Yeah.
Really?
Yeah, no.
Yeah. So if I bring some in the next class, you can separate it for me. All right. Okay. We'll see so. But I think it's quite difficult to pull it apart. So this is quite strong.
Yeah, need more strong.
More strength, yeah. So it's very strong.
Yeah.
Is that what you're saying?
Yeah, but you can cut it.
You can't? Really? You can pull it apart?
Okay,
No problem. Okay, alright, fine, that's fine. And what about something that's weak? Maybe like thread. You know thread? For like sewing.
Aluminium?
Aluminium's actually quite weak, yeah. If you know like aluminium tinfoil, if you had a sheet of it, you can easily pull it apart. So yeah, aluminium's quite weak as well. Okay, so the next term now is stiffness.
The lower force required to break it.
No, well, stiffness is to do with shape. So, for example, stiffness tells us how much it's willing to change its shape or not. You know, so in other words, if something is very stiff, it means it's difficult to change its shape.
Like solids?
Yeah, like solids, yeah, exactly. Now, not all solids are very stiff, though.
Yeah.
Um, the table is pretty stiff, yes. But what about a solid that isn't so stiff? Think like a sponge or something for cleaning.
Yeah.
You know a sponge for cleaning?
SpongeBob.
Yeah, SpongeBob, yeah, exactly. Not quite stiff. So stiffness is how able it is to keep its shape and refuse to change its shape. Okay? So you could say that if something is stiff, it is more difficult to change its shape. So, what example have we seen so far of something that is not stiff?
Paper?
No, like we've done in class. Something that's not stiff.
Coffee.
No. Something we've done that's not stiff. A spring.
Oh.
Yeah, right? A spring is very easy to change its shape, yes? So you say that it's not stiff. And then what would be something that is stiff that we've done? Like maybe a ladder
And some metal.
and metal. Yeah. Some types of metal.
Mm.
So anyways, an example of stiffness is the spring. Is the spring stiff or not stiff?
Steps.
Not stiff. Not stiff, okay? Is it strong or not strong?
Strong.
Strong.
Well, it depends on the spring. Like if I have metal, is it strong?
Yeah.
Yeah, but if I have rubber band, is that
No.
strong?
Mm.
No. So you can have a spring that's strong or not strong, but generally springs are not stiff.
Okay, in the exam, the question should have that if a spring is strong or not. We have to write.
Well, they should tell you what type of spring it is. Like they say a metal spring. That would like a copper spring or something like this. But if they said like a rubber spring,
So easy.
it'd be easy to break, so not strong.
Not strong.
Okay, so next one now.
And the spring is stiffness, right?
What's the problem?
The spring is stiffness.
The spring is not stiff.
Not stiff. Okay.
Yeah. The spring is usually always not stiff, but it can be strong or not strong. Okay, ductility next. What do we think this is? Well, I'd be very impressed if anybody knew this.
First time.
First time, yes. Does anyone know it?
I saw this last year.
You saw it? Do you want to have a guess of what it means?
No, that's why I'm here.
Very good. Right, so this means how easy it is to change the shape into something useful. So can we think of any examples of things that we like to change the shape into making it something more useful for us? Yeah, what? Yeah, blue tack, but I'm thinking of something a bit more useful, stronger, yeah. Yeah? Can we think of anything? Cooper, you know, or copper. Yeah, okay, copper. Well, cooper is also something you could say as well. Copper is something that you can put into different shapes to make it something useful for you. But no, the interesting one you said about cooper as well.
The aluminium.
Aluminium's good too.
The shape to save the food.
Oh yeah, very good. Yeah, yeah. You can make it any shape you want, and it won't crack. It won't break. Now, does anybody know what a cooper is?
Yeah, that's material.
No, that's copper.
Yeah.
I'm talking about a cooper. Do you know who this is? I'll give you an example, okay? Do you ever look at old big wooden barrels? They put beer inside it. Do you know what I'm talking about? Or maybe I'll try and draw it for you.
Yeah, okay.
Really?
Yeah,
My
okay.
drawing is that good?
Old movies.
Yeah, old movies, yeah. So you have like the wood going down like this. And then you have a metal bar going across like this.
Yeah.
Old Western movies, yeah?
Even Tom and Jerry.
Even Tom and Jerry, yeah. Now, what's this made out of?
Wood.
Wood. Now, what shape is this? Is it straight or is it curved?
Curved.
It's curved, yeah? Now, does wood grow straight or curved? It goes straight. You get the wood like this.
Yeah.
And then what do they do to the wood? They slowly bend it into this shape. Now, does it break? No, it doesn't break if you do it carefully. So what would you need to do to make sure you can bend it carefully? You have to move it slowly. Like maybe over a few days. But if you're very careful, you can change the shape from this into this. And this shape is better for you. So this means being able to change something into a shape you want without breaking it. So it's how useful it is to you. Do you understand?
Yeah.
And this is a good example of it. Okay? But we have lots of other ones we do. So, how easy it is to change. Yeah, well, I'm kind of giving you informal definitions for now because I just want you to get used to the words. Okay, how easy it is to change the shape into what you want. Something like this. Okay, without breaking, of course. Okay. Right, the last key word here. Again, this is a word you probably know from English. Tough. What does this mean?
Strong.
Yeah, but you see, we already have the word strong here. Now you're right, in English, tough would just mean strong.
Mean hard.
Yeah, now we're getting closer to it. So tough is like hard. Anything else? Tough is like hard, but there's something special about it.
Yeah, for same.
Sure. Right. So tough is like hard, but what's special about something being tough is that it won't crack and break like for example, can you tell me, hey, give me an example of something that as soon as you try to change its shape, it cracks completely. Glass, yeah, glass. If you take some glass and just start to try to change its shape, what happens? Shatters. Now, can we have something that it's easy to change, or you can change its shape, but it won't really break so much?
The glass when you heat it?
Yeah, if you heat up the glass. Now, actually, we'll be talking about that later, about changing the properties by heating up stuff. But just normal room temperature things.
Play-Doh thing.
Yeah, not the Play-Doh.
Yeah, but I want something hard.
Glue stamp.
No, something hard.
That's fine.
Like the example I did with the wood.
Okay.
You can change it and it won't crack.
Yeah.
Yeah. But I think the example that they give here,
This metal, that's the heater.
steel is an example here.
That's heater.
The heater.
Yeah.
Yeah,
They
like
change the shape.
yeah, like they have on the top that it's curved. It wasn't always
I could
curved.
take this.
Hmm?
I could take those.
Take it out. Yeah, sure.
Yeah.
Take.
I'm
I'm-
put them on floor. Are you
I'm
going?
going.
I thought you put them. in.
Oh no, no.
Oh,
Okay.
Stephen.
Yes.
Can I have a word with August?
Yeah, go ahead.
August, can you come out here and explain it?
that was nice.
Yeah, explain it, please. Okay, thank you.
No problem. Okay. Right. So as I was saying, tough does not crack readily. Do you know what I mean by crack?
Yeah.
Shatter.
Yeah, shatter, yeah. So like the glass. If I try to bend the glass, it cracks.
Yeah.
But if I have a sheet of metal or a sheet of wood, if I try to bend it, it'll be okay. It won't crack. Now wood can crack sometimes. Have you ever seen wood crack? If you bend it.
I would say that.
The gyps, you
Huh?
put on your leg, you have a broken leg.
Yeah.
The gyps.
Steel is very good. With steel you can bend it and it won't really
Won't
crack.
Yeah.
Yeah, but wood can sometimes crack. So I think steel is tougher than wood.
I think wood easily cracks.
Yeah, sure.
Yeah, well, I think it actually depends on the type of wood too. Some wood can bend more than others. I think maybe oak is probably difficult
More
to bend.
expensive.
Yeah, that's more expensive wood too. Yeah. Okay. Now we're going to have two new formulas, but they're simple formulas. The title was stress and strain. So stress. There's an exact definition for stress.
We have pressure? Like pressure?
It's very good. It's like pressure. Actually, it is pressure. Actually,
Stuff.
Pure.
it's force
It's going right with stuff.
Doesn't crack really.
over area,
Yeah.
which is what was this force over area?
F over S.
F over A,
S.
which we said is pressure.
Oh yeah. P.
So if you have like let's say here is your rope.
It's rho or P?
No, it's P. Rho is for density.
That's it.
Now let's say we have something here and we pull here with force F, and let's say the area here is A. Well then the stress is just going to be F over A. Okay?
Yeah.
So it is exactly like pressure. Now the next thing is strain.
What?
Strain.
You mean the long?
No, not train. Strain. August, come this way. There's no cable. This way. You won't die the other way.
Yeah.
All right. Strain. The formula for strain.
Stress over area.
Now you're thinking of something else now. Extension over natural length.
It's extension.
Extension. We had this in simple harmonic motion. What's
I
extension?
heard about it, but I forget.
Oh,
K.
That's K?
K or L. Is it?
Yeah, okay.
yes. Now extension. What's extension?
It's nature?
Uh,
Natural.
Natural length.
Where's the R?
Extension is
Where's
how.
the R?
How long?
It's
it
here in the middle.
Yeah, that's R. Okay, now it's R.
Oh. Right. Extension. Jing dong. Go for it.
Extension means how long to extend.
Yeah. But try to explain extension without using the word extend.
What?
Try to explain extension without using the word extend.
Without using.
Yes, without using the word extend.
The length difference.
Yeah, Mr. Stephen?
Yes, extension is the difference between the current length and the natural length. That's the extension.
Just a second, and for the ductility?
Ductility, yes?
Yeah, that's the metal that's in your hand. This one.
This one.
Yeah, this metal.
Yeah, that's very ductile. Yeah. Okay, extension is how far past it is the natural length. Shh, hey, so say I have a spring and its natural length is 1 meter and it's currently 1.1 meters. What's the strain?
0.1
Over
over 1.
which equals 0.1.
0.1.
Why is 0.1? Because it's 1 1.
That's the natural length and that's the current length. It's not a crazy formula. Are we okay with this?
Yeah.
I really hope so. Really, really hope so. Alright, let's look at the units. So, for stress, what's the units?
No, N over
Force over area.
N
So,
over
newtons over
Oh,
meters squared.
Sorry.
Now, what's the strain?
strain is the extension
Yeah, what's the units?
N over
Meter.
N over
Meter over
L, a meter.
meter, which means no unit.
Nothing.
There's one thing we've done in physics so far that does not have a unit like this.
The R.
Not the or.
Mu, sorry.
Huh?
Mu.
Oh, very good. 2 things then. So mu is the first one. What's the other thing that doesn't have a unit? Very good though, mu.
X? No, XN.
Yeah. Do we remember?
No.
Do you remember specific gravity or relative density? Remember relative density?
The center of the gravity.
No. Does anybody remember this? S equals density over density of water.
Yeah.
Yeah, okay.
That has no units also. Same as mu. Both have no units.
Okay.
Sorry, Mr.
Yeah.
S equals what?
Density over density of water.
Density.
Density. Remember?
Rho.
D or T?
Rho. Not P, not T. It's this letter. No. In a minute or two, okay? I know you have a class at 3, but I just want to get to the formula now. So there's something called Young's. Oh, you remember this?
Yeah.
Very good. Young's modulus. And Young's modulus, the formula for this is stress over strain. So this is important now. Everything I've done so far is just to give you this definition. So this is very, very important. You will most certainly see this in the exam, or at least in one of your experiments we'll do in January, okay? So very, very important.
Okay.
No, don't close your
No,
book.
I'm not closing.
So I'm sorry,
So I'm just making my day.
Oh my goodness. Okay. Let me see. Yeah, the only thing I'll say is for a if I have a material, let's say, Shingon, come on. Here's my spring. Okay? And let's say I move it. So now it has some stress. What's the formula for stress? It's force over area. So let's say this is the area here. Okay? Let's say it's like some kind of spring cable or something. Yeah, no, yeah, you're right, but we won't use that just yet. And we also have strain. And that's the extension. So let's say it starts here, and the natural length is L, and then I move it a little piece. I'll call it delta X. So what's the Young's modulus? That's going to be stress over strain. And strain will be this.
Delta X over L.
Yeah. So if you want, you can say that's F over A times L over delta X.
Yeah, yeah.
And what you'll notice is this is always the same. So if I move this more, does the stress increase?
Yeah.
And does the strain increase?
Yeah.
Yes. But this here doesn't change. So it says here, this constant is called the Young modulus, and the letter you use for it is capital E.
For what?
Capital E. That's the Young's modulus. Okay. If the material has a large E, it is difficult to change its shape. So again, if E is very large, it's very difficult to change its shape. So like here,
Stiffness.
yeah, it's related to that, yeah. So this table, big E or small E?
Big.
Big E. But this paper cup,
Small.
small e. And we might do an experiment to calculate this. But I think it's probably best if we look at this a bit more next time. Yeah, there's some experiments here with copper and glass and rubber and steel. Yeah. Now, I think what's likely to happen tomorrow is, because this is a big chapter,
Tomorrow we don't have.
I mean Wednesday, it'll probably take me 1 or 2 classes to just cover this chapter and then give you a worksheet. So there'll be a lot of lecture material in the next class, okay?
No formula.
Huh?
No
Well, it's a
questions.
couple, but not many.
No questions doing.
Oh, questions will be at the end of the class. I have, look, I have beautiful page of questions here to do at the end. Okay? Anyways, if you found that a little bit difficult, what page is it on in the book?
168. 168.
You're so way off, man. What page is it on?
26.
168. I think you're still thinking of the periodic time from the pendulum was 1.69, possibly. All right.
What page is it?
Huh?
What page? 36, yeah.
At least something.
Can we roll?